Today we are going to solve the problem 5.8 of Griffith third edition Introduction to Quantum Mechanics. The problem 5.8 is suppose you had three particles, one in state psi a of x, one in the state of psi p of x, and another one is in the state psi c x. Assuming psi a, psi b, and psi c are orthonormal, construct the three particle state representing the distinguishable particles P identical boson, C identical fermion. First, we will see distinguishable particle. The total wave function is product of individual wave function psi a at x1, psi b at x2, psi c at x3. I have represented this psi 1, 2, 3. First one is for A, second one is for B, third one is for C. So this is x1, x2, x3. This is a very simple quadratic product. Then you can distinguish the particle A from P and P from C. Mutually, you can distinguish each other. So if you put a tag, you can trace the particle where it is. So the total wave function is a simple product of these three wave functions. So we can this is the wave function for distinguishable particle. Then we will move on to identical boson and identical fermion. Now we will see for the identical boson, that is section P, the total wave function capital psi sub x is equal to 1 over square root of 3 factorial, because the number of particles is 3, which is equal to summation over the P represent permutation combination, and P operator P is the permutation operator, so it acts on psi sub a of x1, psi sub p of x2, and psi sub c of x3. So as I said, where the operator P is the permutation operator, and where all the sum is over all possible permutation. So here the symmetric wave function S represent symmetric, because any number of boson will have the same energy state. So this can be if you apply all permutation state, you will get the symmetric wave function like this. Here I have used a shorthand form. Here, for example, psi x 1, 2, 3 means first letter represents A, second letter represent B, third one represent C. This is C. So here the meaning of this term is psi A is at x1 state, and psi P is at x2 state, and psi C is x3 state. I have written it in the simple mathematical form. Say for example, if you take this one, this is first letter is for A, second one is for B, and third one is for C. The meaning of this expression is here psi A is at x3 state, because first letter is 3, and psi B is x1, P is x1 state, and psi C, that is psi C, third one, is equal to at x2 state. So this is the meaning of this shorthand form. For to write it in an elegant way, I have used this symbol. Hope now you can understand this all permutation combination. Here A is at x1, B is at x3, C is at x2 state. So it goes on like this. And then we will move on to identical permeability. Now section C is for identical fermion. we have to find the wave function. Like boson, we have seen the psi sub s, that is symmetrical one. For fermion, it is a anti-symmetric one. So for identical fermion, we have to use the Slater determinant. I have explained about the Slater determinant in my theoretical lecture. So Slater determinant, for example, if you take the first row, first column, you can multiply this and this, and that is 2 and 3 plus, and 2 and 3, it will become naturally minus. See, this here the particle P is at x2, particle C is at x3. We are interchanging. Here particle C is at x2, P is at x3. So when you interchange naturally from determinant matrix property, it will become, when you change the particle, it will become minus. So naturally it is antisymmetric. Here you have 1 over square root of n factorial. N factorial is 1 over 6. Now if you multiply, say for example, I am taking psi a1, and if you multiply P and C, see here, as I said already, the first letter is for A, second letter is for P, third letter is for C. So I am writing this in a shorthand form. For first, you can multiply this psi a at x1, psi a at x1, position x1. Here you can see psi a at x1. This is x1. Then psi b at x3. Sorry, x2. Psi c at x3. Then if you multiply this and this, naturally sign will get changed. This is A, this is P, and this is C. Now you have minus psi A x1. First one is x1. We are not changing. Then psi P is x3, not x2. And psi C is x2. So now you can notice uh, we are interchanging the state psi p x1 and psi 2 x3. We are interchanging x2 and x3. So x2 and x3 got interchanged. So because of antisymmetry property, now automatically this negative sign comes over here. So this is the antisymmetric wave function for identical fermion. So here this is the important properties of Slater determinant. Thank you very much for watching my video and supporting me continuously. Thank you very much.